So now we're moving on to the second part of this, in which we're talking about a cooling tower. Water coming down and then throughout, and then we have a temperature of air in this case, and calling it TG for temperature of the gas, and we have gas flowing in, and we're going to call the water flow rate, or L for liquid. We're going to define that as kilograms per second, and we're going to say the gas flow rate is also in kilograms per second. And we're starting at the top, and we're setting z equal to 0 at the top, and that in the positive z direction would be moving down the tower. And in this tower we have a section, in which case this packed section has a specific area of squared per cubic meter, and this packed area also has a cross-sectional area of square meters. And then we're also saying that the change in z is just along this line. dz is just somewhere along that line, or the change in z. And we want to find three differential equations along this line. And we're going to start out with dy dz, which is how is the mole fraction of water changing with respect to z. So as we go down the cooling tower, how is the mole fraction of water changing? So essentially we're doing a differential, so we're going to be starting with the change, and we're going to say the change in, and we're going to say the gas flow rate, G, and then we're going to multiply that by the mole fraction of water, how many moles of water there are in the air, and then we're going to divide by the molecular weight, and that's going to give us moles per second. And we're going to set that equal to the mass transfer, in which case mass transfer is driven by the difference in concentrations of water from the top and the bottom. And we're going to say that's equal to the mass transfer coefficient times the concentration at the surface minus the concentration. So there's essentially the differences in concentrations. And this is all happening over a defined area, or a given volume. And this is where the specific volume and the cross-sectional area taking place for the pack section here. And we need to know that over what volume is this happening. So that will be the specific area, or how much area packing, so meters squared per meter cubed there is. So, and then we're going to multiply that by how much cross-sectional area there is to give us a volume. And then that is going to be changing with respect to z. So that gives us our differential equation. And again, we're looking for how does y change with position to z. So what you may notice is that we have a cross-sectional area A here, but we don't have it on our left side. And we're going to have to keep bringing A through the equation with us the longer we go. However, if we change our flow rates to include that cross-sectional area, L and G, to include this cross-sectional area, there's no need to keep dragging throughout the equation. So we're going to go ahead and do that and say that our gas flow rates for L and G are now in terms of kilograms per meter squared second instead of just kilograms per second. And then we're going to add a cross-sectional area to the left side as well, and then in that way both cross-sectional areas will cancel out. You don't have to keep dragging it through our equations. So now we're going to try and find dy dz, or how the mole fraction of y changes with position in the cooling tower column. So what we can do is we can assume, what we want to do is we want to assume that the gas flow rate over the molecular weight is going to remain constant, and that is not going to be affected by the positioning, so we can take it out of the derivative in that case. So we can say gas flow rate over the molecular weight is outside of the derivative, because it's not being affected by the change in the position of the cooling tower. We're just going to assume that remains constant. Oh, I also forgot that we need to remember that air is flowing up through the column, which is negative, and it's in the negative z direction, so we have to make sure that the mass transfer is negative, because as the air flows up, it is going, since we described positive z as going down the column, negative z must be going up the column. So our mass transfer coefficient must be negative there in front to for our described problem. I'm trying to get out words here. Back to where I was. Negative Kc stays here. Difference in concentration remains, and now we just have the specific area, and then with respect to the change in z. So now we want to divide dz over and then get the mass flow rate and molecular weight onto the other side. So we can say dy dz, or the change in the mole fraction of water with respect to position in the column, is equal to the negative mass transfer coefficient, change in concentration. We can also do this at the same time, no reason. Leave it there. We're going to change the concentrations into partial pressures. That way, we're just, because that's what we've done in the past, and it's going to allow us to describe the equation as a flux, as you'll see. So concentrations are simply just at the surface, it's going to be the saturated partial pressure of water at that given temperature Tw, because it's at the surface, it's going to be a saturated temperature over RT. And then we're going to subtract, in this case, the concentration of the infinity is concentration of water in the air, and that's going to be the total pressure times the mole fraction of the water over RT. Then again, like I said, we're going to bring the molecular weight and the gas flow rate over. So that's what we get for our equation. And then we're just going to go ahead and say that this is going to be our molar flux of water. And so that equation further simplified into dy to z is equal to negative molar flux of water times the specific area times the molecular weight over the gas flow rate. So that gives us our first differential equation, which is dy to z, which is how does the mole fraction of water change with respect to z, or the positioning in the cooling tower. So now we're moving on to the second differential equation that we want to find from this cooling tower, and that is going to be how does the temperature of the water change with respect to position in the cooling tower. And immediately when we're thinking of a change in temperature of the water, we can use enthalpies or enthalpy equations to see how the temperature, the change in temperature is changing in enthalpies. So essentially we can start by saying that the change in enthalpy of the water is equal to, and then the change in enthalpy or energy of the water is going to be equal to some flow rate times heat capacity. So in this case, that flow rate is going to be L, and then times the heat capacity of the liquid, which is Cl, and then that's going to happen over a change in temperature. And then we're going to have to add the cross-sectional area here as well, because that's happening over a specific area. And then we can set that equal to the heat coming in, the heat transfer in two ways. We have the heat transfer from the air to the water, and then we also have the heat from evaporation causing the change in temperature. So we're looking at what causes the change in temperature. We have heat from the air to the liquid, and then we also have the heat of vaporization of the water. So those are going to be our two major terms of this next equation. So let's start with the heat from the air going into the water, and we're going to start by saying the heat transfer coefficient H times the driving force is going to be the change in temperatures. So the temperature of the gas, in this case air, and then minus the temperature of the water, and that is happening. There's going to be again we have to do what volume that's happening over. So that's going to be the specific area times the cross-sectional area, and then it's going to be with respect to changing position. Because again, it happens over a specific volume, so that gives us over what volume that heat transfer is happening, and then again that's the heat from the air to the water. And now we also have to account for the term where the heat from evaporation of the water is called temperature change, and we're going to have to subtract from that the heat of vaporization times the flux, the molar flux of water. And then again, that's happening over area and then volume with respect to the change in position, or dz. And from there, we can pull out the equation and say, look for our differential equation, which is what we want to know. How does the temperature of the water change with respect to position in the cooling tower? and we can say that right here you can pull a dz out of both of these and then divide to the other side, and then divide the cross-sectional area is canceled out because it's in all terms, and then we can say divide the flow rate of the water and the heat capacity of the water over to the right side as well to isolate the change in temperature water over the change in distance is going to be equal to, and it's going to be equal to the specific area over that flow rate times the heat capacity of the liquid. In this case, it's water. So the specific area of the packing over the liquid flow rate of the water and the heat capacity of the water, and that's going to be the rest of the equation, which is going to be the heat transfer coefficient times the driving force, which is temperature of the air minus temperature of water, and then that's going to be subtracted from the heat of vaporization times that molar flux of water. So again, we started out by saying that the change in temperature was due to a change, or there's a change in temperature, therefore there's a change in enthalpy, and that change in enthalpy is a flow rate times the heat capacity times that change in temperature, and then that change in temperature occurs because of two reasons. We have a change in temperature because there's heat transfer from the air to the water, and we also have a change in temperature due from the heat of vaporization causing the water to go into the air. So that's why our two terms come from here: the heat transfer from water or from the heat from the air going into the water, as well as the heat causing the evaporation. And that gives us our second differential equation. How does the temperature of the water change with respect to position in the cooling tower? So now we're moving on to our third differential equation, which is how does the temperature of the gas or temperature of the air change with position in the cooling tower. So we know this one. We know how we know the differential equation for how the mole fraction of water changes with position, and we know how the temperature of water changes with respect to the change in position of the cooling tower. Now we're trying to find out this one. So what we need to do to figure out the change in temperature of the air with respect to position is essentially look at a single section of this cooling tower and say that a single section of this cooling tower has a change in distance z, so dz, and then in this you got the enthalpy of water going down through it, and you got the enthalpy of the gas or air going up through it. And we know, because this problem was said to be steady state, that enthalpy of the water going down and minus the enthalpy of the gas going up has to be equal to 0. So we know that the change in the enthalpy of the water minus the enthalpy of the air is equal to 0. And that's big, because then it allows us to say that the change in enthalpy of the water is equal to the change in the enthalpy of the gas. And we already know this from last part. We just found the change in the enthalpy of the water. So now we have to find the change of the enthalpy of the gas and set that equal to the change of the enthalpy in the water to help us find how the temperature of the gas changes with position. So we're going to start out by, again, saying that the change in the enthalpy of the gas is equal to, again, a flow rate times a heat capacity. So it's going to be the gas flow rate times the heat capacity of a gas. And then that is going to be times the cross-sectional area. And then also we're going to multiply by the temperature of the gas. So now we also need to account for the enthalpy of vaporization of the water. So we need to add the heat, or the flow rate of the gas, times the area, and that is going to give us moles per second. So we need to divide by molecular weight. We need to divide by molecular weight to get moles per second, because that gives us kilograms. And then we're going to multiply by the mole fraction of water, Y. And then this is the heat vaporization, or the enthalpy of vaporization for water. So we need to add our lambda, or heat of vaporization, to the front of that. To the front of that equation. So now we can say that that is, and we're looking for how does that change with respect to position. So we need to do that. So we need to differentiate that. And then we're going to set that equal to, and then like I said, it's steady state, so we know that the enthalpy of the water going down is equal to, is equal to the enthalpy of the gas going up. So we found the water back up here, and we're just going to drag this equation down here, say that the heat transfer coefficient times the driving force of temperature difference between the gas and the water times the specific area times the cross-sectional area times dz, or the change in position, minus the heat of vaporization, molar flux of water, times the specific area times cross-sectional area times dz. Again, you don't really have to carry around a all the time because it always cancels out. So this cross-sectional area of the packing is going to cancel out again, and you're left with this equation that we're going to go ahead and solve for the change in temperature of gas with respect to position. So once again, we're going to assume what things can remain constant and don't have to remain inside that derivative. So we want to assume that the gas flow rate and the specific heat capacity for the gas, or the heat capacity for the gas, are going to remain constant no matter where you are in the cooling tower, and therefore they don't need to be inside the derivative, as well as the heat capacity, or the heat of vaporization, the gas flow rate, and the molecular weight for this as well. But we do know that Y, the molecular or the mole fraction of water, does change with position. So what we're going to do is we're going to pull out the gas flow rate times the heat capacity of the gas, but keep in the temperature of the gas because we know that's changing with position in the tower because it is a cooling tower. And then we're going to add heat of vaporization, gas flow rate, molecular weight, times dy, which is the change in mole fraction. So now that we have that, we're going to look at the other side of the equation, set that equal to, and then we're going to look, we can go ahead and divide dz by both these terms here and cancel it out on the other side. So we are solving for that right there. And then dz would go away. And we're left with h, heat transfer coefficient, times the driving force of temperature differences times the specific area, minus heat of vaporization, molar flux of water, times that specific area. So now that we have that, we can look at what else do we know about this problem. Well, we know that we already found that the change in mole fraction of water with respect to position in that cooling tower, dy dz, is something that we found up here, right there. That's our first differential equation. So if we look at what dy dz is equal to, it's equal to the negative molar flux of water times the specific area times the molecular weight over the gas flow rate. So if we look at if we plug that in for dy dz, it would actually cancel out this term dy dz and this term over here, this negative heat of vaporization, molar flux of water times the specific area. So we can go ahead and, if we plug dy dz in there, it would cancel out this term, as well as that term if we plugged it in. So now we have the gas flow rate times the specific heat of the gas times the change in temperature of the gas with respect to position in the cooling tower, equal to the heat transfer coefficient times the driving force of difference of temperatures between the gas and the air and the water, times the specific area A. And the only thing left to do would be to divide by the gas flow rate and the specific heat, or the heat capacity of the gas. And then that we can find our third differential equation, which is the change in the temperature of the gas or the air with respect to the position in the cooling tower, is equal to the heat transfer coefficient times the specific volume divided by the gas flow rate times the specific heat of the heat capacity of the gas, times that driving force, or that difference in temperature between the air and the water. So now that we have found this, we have found our first differential equation here, our second differential equation here, and our third differential equation here. So now that we have our three differential equations, oh my god, I wasn't even around. Get out of the way. There we go. Okay, so we we have our three differential equations, 1, 2, and 3, and so we have now found out how the mole fraction of water changes with respect to position, how the temperature of water and how the temperature of gas change in respect to position of where they are in that cooling tower. And now we're going to switch over to Python and code out a specific scenario, in which case we're going to use these differential equations and actual numbers to solve a problem.